basic electricity and electronics, alternating current. Inductors and inductive reactance. You have learned that magnetism can be produced by passing an electric current through a conductor. The reverse of this is also true. A conductor which moves across or cuts a magnetic field develops a flow of electrons. To demonstrate this principle, a zero-center micrometer is connected across a single conductor. With no induced voltage, the meter pointer rests on 0 at the center of the scale. As the wire is passed downward through a strong magnetic field, the meter pointer moves to the right, indicating an electron flow in one direction. The wire is now passed upward, cutting the magnetic field in the opposite direction. The meter pointer now moves to the left of center, indicating an electron flow in the opposite direction. If the wire is passed downward but at a faster rate, the meter reads to the right but at a higher value. This indicates that there is a greater electron flow produced by cutting the magnetic field faster. Holding the wire steady, the magnet is now passed over the wire in an upward direction. The meter indicates that there is an electron flow in the wire.
When a voltage is developed in a wire that is either cutting or being cut by a magnetic field, the process is called electromagnetic induction. In Figure A, a small current flows through a conductor and produces a magnetic field around it. As the current flow increases, as shown in B and C, the magnetic field becomes stronger and expands outward from the inductor. When the current flow decreases, the magnetic field contracts toward the conductor. This is shown in D and E. The magnetic field induces a voltage in the conductor as it is expanding, as shown in A and B. But no voltage is induced when the field stops changing, as shown in C. As the magnetic field contracts toward the inductor, a voltage is induced in the conductor in the opposite direction. This is shown in drawing D and E. This process of inducing a voltage in a conductor when the current is changing in that conductor is called self-induction. The voltage induced by self-induction is called a counter-electromotive force, abbreviated CEMF. This induced voltage always opposes the applied voltage causing the action. That is, they are 180 degrees out of phase. Self-induction in a coil is much greater because of the concentration of the magnetic flux. When there is a variation of current in the coil, the magnetic field also varies, expanding as the current increases and contracting as the current decreases. The magnetic lines of force cut any conductor that is within their range and induce a voltage that is always in a direction to oppose the current change. The ability of a circuit to produce a voltage by electromagnetic induction when the current changes is known as inductance. The symbol for inductance is a capital L. The unit of measurement for inductance is the Henry, abbreviated capital H, named for the American physicist Joseph Henry, who discovered the voltage caused by self-induction. An inductance of 5 Henrys would be written L equals 5H. By definition, the Henry is the amount of inductance which induces a counter-EMF of 1 volt when the current is changing at the rate of 1 ampere per second. The Henry is a large unit of measurement. For many practical applications, 2 smaller units are employed. One is the millihenry, abbreviated small m, capital H. A millihenry is equal to 1,000th of a henry, a 3-place decimal. And the other is the microhenry, abbreviated small u, capital H. A microhenry is equal to 1/1,000,000th of a henry. This is a 6th-place decimal. It is often desirable in electrical and electronic circuits to take advantage of the properties of inductance. This is done by a device called an inductor, which is a coil made to have a specific inductance value. Inductors are classified according to the type of core on which the coil is wound. The type of core used in an inductor is important because it affects the strength of the magnetic field around the coil. All electromagnetic relays or applications requiring a strong magnetic field employ iron core inductors. An iron core inductor is represented schematically by a coil symbol with 2 lines next to and parallel to the axis line to indicate the presence of an iron core. The air core inductor is a coil of wire usually formed around a cylinder of some non-magnetic material such as cardboard. This material serves no other purpose than to hold the shape of the coil. The schematic symbol for an air core inductor is a coil without parallel lines. The symbol remains the same regardless of the type of winding or the number of turns involved. The inductors used in high-frequency circuits, such as those in radios and television sets, usually have air cores because of the high power losses at these frequencies. When an inductor is connected to an AC source, the current is changing continuously. The inductance of the coil will oppose that change in current by the self-induction of a counter EMF. The amount of opposition offered by an inductor is called inductive reactance. The symbol for inductive reactance is a capital X subscript L. Since the magnitude of induced EMF depends on the amount of inductance and the frequency or rate of change of the current, the formula for inductive reactance takes both into account. Inductive reactance, X subscript L, equals 2 pi FL. The 2 pi F represents the rate of change of the current. There are 2 pi, which is equal to 6.28 radians in a cycle. Therefore, 2 pi F represents the rate of change in current per second, or angular velocity. The frequency F is in hertz, and L is equal to the inductance in henries.
Now let's solve some problems concerning inductive reactance to better understand this type of opposition to current flow. In the circuit shown, assume that the resistance of the inductor is 0 ohms. The frequency of the voltage source is 60 hertz, and the inductor, L, is a 10 Henry coil. Substituting the values in the basic formula for inductive reactance, you obtain XL equals 2 pi FL. XL equals 6.28 times 60 times 10. Solving the equation, the inductive reactance equals 3,768 ohms.
Using the same circuit and keeping the inductance L fixed at 10 henries, the voltage source frequency is doubled to 120 hertz. Substituting the values in the formula, you obtain X subscript L equals 2 pi FL. X subscript L equals 6.28 times 120 times 10. X subscript L equals 7,536 ohms. Notice that the doubling of the circuit frequency doubled the inductive reactance. If the frequency was changed to 30 hertz, the inductive reactance would be reduced to half, or 1,884 ohms. The same would be true if the frequency were held steady and the inductance was increased. As the inductance is doubled, the inductive reactance is doubled. Comparing these two circuits, The circuit on the left with the 10 Henry coil has an inductive reactance of 3,768 ohms. By increasing the inductance to 20 Henrys, as shown in the circuit on the right, the inductive reactance was doubled to 7,536 ohms. The inductive reactance varies directly with the frequency and with the inductance. Now let's analyze the waveform of the voltages and current in an ideal inductance when connected to an AC source. An ideal inductance is a theoretical coil that has zero resistance. The current in an inductive circuit takes the form of a sine wave if the applied voltage is of a sine wave form. Remember, the greatest rate of change in a sine wave form occurs when the waveform passes through its 0, 180, and 360 degree points. The least rate of change occurs at its 90 degree and 270 degree points. Since the maximum counter EMF is induced when the current is changing at its greatest rate, and the counter EMF is 0 when the current waveform is at maximum, the counter EMF waveform can be constructed as shown. Notice, there is a 90-degree phase difference between the current in an inductive circuit and the counter EMF it produces. You have learned that the counter EMF induced always opposes the applied voltage, and that they are 180 degrees out of phase. By constructing the waveform of the applied voltage using green ink, you will notice that there is a 90-degree phase difference between the current and the applied voltage. In a pure inductive circuit, the current lags the applied voltage by 90 degrees.
Now let's review some of the highlights of this program. Electromagnetic induction is the process of inducing a voltage in a conductor which is cutting or being cut by a magnetic field. The voltage induced by self-induction is called counter-electromotive force, CEMF.
The inductance is the ability of a circuit to produce a voltage by electromagnetic induction when the current is changing. The symbol for inductance is capital L. The unit of measure of inductance is the Henry, symbol capital H.
Inductive reactance is the opposition offered by an inductance to a change in current flow. The symbol is XL. Be sure to view this program at least once again. It is important that you understand these fundamental concepts of inductors and inductive reactance.